For most people, black holes arrive as a bundle of half-true ideas. They are presented as cosmic vacuum cleaners, as literal holes in space, as eternal prisons where time stops and information dies. Movies turn them into portals. Popular science turns them into cartoons. Even good classroom explanations often rely on shortcuts that are useful at first and misleading later. And that is understandable, because black holes are genuinely hard to talk about. They live at the boundary between general relativity and quantum theory. They force us to think about gravity, thermodynamics, information, causality, and the shape of spacetime all at once. The closer you get to the real physics, the less they behave like everyday objects, and the more they begin to expose the limits of ordinary intuition. But there is a difference between a simplification and a misconception. A simplification is a temporary bridge. It helps you cross from confusion to clarity. A misconception is something you keep long after it has stopped helping you. It lingers in your mental picture and quietly distorts everything else built on top of it. That is exactly what has happened with black holes. So in this documentary, we are going to do something slow and careful. We are going to take 33 of the most common black hole myths and misconceptions, one by one, and replace them with the best modern picture we have. Not every question is settled. In fact, some of the deepest ones remain open. We still do not have a complete theory of quantum gravity. We still debate what the black hole interior really means. We still argue about the most elegant resolution of the information paradox. We still do not fully understand how the earliest supermassive black holes appeared so quickly in the young universe. But uncertainty is not ignorance, and open questions are not failure. In black hole physics, uncertainty is often where the most interesting science lives. The last decade has transformed the field. The Event Horizon Telescope gave humanity its first image of a black hole shadow. Gravitational wave observatories turned black hole mergers from theory into repeated observation. The James Webb Space Telescope began showing us unexpectedly massive black holes and galaxies very early in cosmic history. And theoretical work on Hawking radiation, entanglement, Page curves, and quantum extremal surfaces has sharpened the information problem in ways that would have sounded almost surreal to an earlier generation of physicists. So this is not a story about black holes as they were commonly described 50 years ago. It is a story about black holes as a modern viewer should understand them now, as real astronomical objects, as thermodynamic systems, as engines of extreme astrophysics, and as some of the most revealing test cases in all of fundamental physics. There is another reason to take this subject seriously. Black holes are not merely exotic objects hidden in deep space. They are natural consequences of Einstein's theory of gravity. If the universe contains enough mass in a small enough region, and if nothing stops the collapse, a black hole can form. That means black holes are not exceptions to the laws of nature. They are one of the clearest demonstrations of those laws under extreme conditions. And because of that, every mistake we make about black holes tends to produce a deeper misunderstanding about the universe itself. Get gravity wrong, and black holes become vacuum cleaners. Get spacetime wrong, and black holes become literal holes. Get thermodynamics wrong, and black holes become frozen, eternal voids. Get relativity wrong, and time somehow stops in a way that sounds mystical rather than geometric. Get quantum theory wrong, and we fall into dramatic claims about information being erased, as though physics had casually abandoned one of its most powerful principles. So our task here is not just to tidy up a few myths. It is to rebuild a mental model. We are going to move from the broadest misunderstandings toward the deepest ones. We will begin with gravity, the event horizon, light, and tidal forces. Then we will move into evaporation, information, and the origin of black holes across cosmic history. After that, we will talk about mergers, primordial black holes, gravitational waves, and the environments around active galactic nuclei. And finally, we will end with the biggest open questions: the singularity, the interior, quantum gravity, and the reasons black hole physics is still one of the great frontiers of science. The goal is not to drain the wonder out of black holes. It is the opposite. Because the more accurate the story becomes, the stranger and more beautiful it turns out to be. The popular myths are dramatic, but reality is more elegant. Reality says a black hole can be as massive as billions of suns and yet have an average density lower than water. Reality says you could cross the event horizon of a supermassive black hole without feeling a sudden impact. Reality says black holes can radiate, evaporate, merge, recoil, power quasars, and perhaps preserve information in ways that tie spacetime itself to quantum entanglement. That is not less mysterious than the myths. It is more. So take this as a long-form reset. If you have heard these ideas before, think of this as recalibration. If some of them are completely new, think of this as a guided tour through one of the strangest territories in modern physics. And with that, let us begin where most confusion begins too, with gravity, horizons, and the basic picture. Before we get to information paradoxes and quantum puzzles, we have to fix the foundation. Most black hole myths begin with a misleading image. A black vortex in space behaving like a cosmic drain. That image feels intuitive, but it quietly breaks the logic of gravity. Black holes are extreme, but they do not suspend the basic rules that govern stars, planets, and orbits. They obey those rules. What changes is the scale and the geometry. This first group of myths is about the picture most people carry in their heads when they hear the phrase black hole. Are black holes really holes? Do they instantly destroy anything that touches them? Does time literally stop at the event horizon? Do all black holes behave the same way? Is spaghettification the same thing as crossing the horizon? These questions sound basic, but they matter because each wrong answer points your intuition in the wrong direction. Once you fix the basics, the deeper material becomes much easier to understand. So here, we rebuild the foundation. Myth 1: black holes are cosmic vacuum cleaners that suck everything nearby into oblivion. This is one of the most common misconceptions, and it obscures what gravity actually does near a black hole. When you hear black hole, your brain pictures a cosmic drain, a whirlpool in space pulling everything toward doom. That mental image is wrong at a fundamental level. Black holes do not suck. They do not reach out and grab objects. They do not have any special sucking power that regular stars lack. A black hole with the mass of our sun would have exactly the same gravitational pull as our sun. If the sun suddenly became a black hole right now, Earth would not spiral inward. We would continue our orbit exactly as before. The only difference would be darkness and cold. Gravity does not change based on what type of object you are dealing with. It depends purely on mass and distance. A black hole with 10 solar masses has the same gravitational influence at a given distance as any other 10 solar mass object. The intense gravity only becomes overwhelming when you get extremely close to the event horizon. But that closeness is the key. You have to deliberately get near it. Think about Jupiter. It is far more massive than Earth, yet it has not vacuumed up the rest of the solar system. The Moon has not been vacuumed into Earth despite being relatively close. Gravity follows the inverse square law: double your distance, and the force becomes 4 times weaker. Black holes follow this exact same rule. The confusion comes from the event horizon. Once you cross that boundary, Escape becomes impossible, but you have to cross it first. And crossing it requires getting within a few kilometers of the black hole. If we are talking about a stellar mass black hole that is incredibly close on cosmic scales, the nearest known black holes are still well over 1,000 light-years away. We are in no danger of being sucked in. Here is what actually happens near a black hole. If you are at a safe distance, you can orbit it just like you orbit any star. Stable orbits exist. The International Space Station orbits Earth. Mercury orbits the Sun, and stars orbit the supermassive black hole at the center of our galaxy. Sagittarius A has 4 million solar masses, yet stars near it maintain stable orbits. Some of these stars have been tracked for decades. They loop around the black hole and return, no sucking involved. The myth probably started because we observe black holes consuming matter. We see accretion disks, we see jets. We see stars being torn apart in tidal disruption events. But this happens because matter got too close, not because the black hole reached out and grabbed it. The distinction matters enormously. When a star gets within a certain distance of a supermassive black hole, tidal forces rip it apart. The debris forms an accretion disk and spirals inward. This looks dramatic. It looks like the black hole is feeding. But it is not fundamentally different from Jupiter ripping apart comet Shoemaker-Levy 9 in 1994. Gravity acting on objects that came too close. The real danger of black holes is not that they pull you in from far away. The danger is that if you happen to pass close enough, the tidal forces will destroy you, and if you cross the event horizon, you can never leave. But these are dangers of proximity, not dangers of cosmic vacuum. Myth 2: black holes are literal holes in space. The name itself creates the confusion. When you hear hole, you imagine a tunnel, a gap, an opening to somewhere else. But black holes are not holes at all. They are objects, extremely dense objects with mass concentrated in an impossibly small region. A black hole is not empty space. It is not a void. It is the opposite. It is extreme concentration. All of its mass crushes down to a region smaller than an atom in the classical picture. Some theories suggest it compresses to a mathematical point called a singularity. Other theories suggest quantum effects prevent true singularities. But either way, we are talking about matter, not absence of matter. Think of it this way. Take the entire mass of the Sun. Now compress it down to a sphere with a radius of roughly 3 kilometers. That gives you a solar mass black hole. The mass is still there. Nothing disappeared. It was squeezed into an incredibly small space. The confusion intensifies when people hear about space-time curvature. Einstein's general relativity describes gravity as curved space-time. Massive objects warp the geometry around them. The warping becomes so extreme near a black hole that people imagine space itself has a hole torn in it. But that is not what curved space-time means. Space-time is not a sheet that rips like fabric in a cartoon. When we say a black hole curves space-time, we mean that paths through space and time near the black hole are bent. Light bends, trajectories curve. Distances and durations behave differently, but the space-time manifold remains continuous. Consider a bowling ball on a trampoline. It is not a perfect analogy, but it helps. The ball creates a depression. Smaller objects roll toward it, yet the trampoline does not have a hole. The surface curves but remains intact. Similarly, a black hole warps space-time without creating a literal opening. What makes black holes special is the degree of curvature. Normal stars curve space-time a little bit. Neutron stars curve it far more. Black holes curve it so strongly that at the event horizon, all future-directed paths lead inward. But that is still curvature, not a tear in reality. Some people wonder if black holes connect to other parts of the universe. Could they be tunnels to distant galaxies or even other universes? This idea comes from theoretical solutions to Einstein's equations called wormholes. But wormholes are mathematical possibilities, not confirmed astrophysical objects. Even if they existed, they would require exotic matter with negative energy density to remain open in a traversable way. No such astrophysical structure has been confirmed. Real black holes in our universe do not function as portals. The singularity at the center is not a doorway. It is the point where our present equations signal a breakdown. That tells us we need quantum gravity, not that a tunnel has been found. The term black hole was popularized in the 1960s by physicist John Wheeler. Before that, these objects were sometimes called frozen stars or collapsed stars. Those older names were less dramatic, but in some ways closer to the basic physical myth. 3. All black holes are perfectly black and emit no light. Not exactly. Black holes emit radiation, and the regions around active black holes can be among the brightest places in the universe. In the 1970s, Stephen Hawking showed that black holes are not completely black. Quantum effects near the event horizon allow them to emit thermal radiation. This radiation carries energy away from the black hole. Over extremely long timescales, it causes the black hole to evaporate. Small black holes evaporate faster. Massive black holes evaporate more slowly. But the key idea is that black holes are not completely dark in the thermodynamic sense. This is Hawking radiation. In the standard heuristic picture, quantum fluctuations near the horizon produce particle pairs. Usually such pairs annihilate quickly. But near the horizon, one partner can effectively escape while the other contributes to the black hole's energy loss. For stellar mass black holes, Hawking radiation is unimaginably faint. Their temperatures are far below the cosmic microwave background, so in practice, they absorb more energy from the universe than they emit. That is why astrophysical black holes still appear dark. But Hawking radiation matters because it tells us something profound. A black hole has temperature, it has entropy, it behaves like a thermodynamic object. That alone changed modern physics. And Hawking radiation is not even the main source of light associated with black holes. The accretion disk around an actively feeding black hole can glow ferociously. Matter spiraling inward becomes compressed and heated. It radiates invisible light, ultraviolet, X-rays, and sometimes gamma rays. Some of the brightest known objects in the universe are powered by black holes. Quasars, among the most luminous objects in the universe, are powered by actively feeding supermassive black holes. A single quasar can outshine its host galaxy. Then there are jets. Many black holes, especially in active galactic nuclei, launch jets of particles moving close to the speed of light. These jets can extend for thousands or even millions of light years and radiate across the electromagnetic spectrum. The Event Horizon Telescope released the first image of a black hole's shadow in 2019. The target was the supermassive black hole in the galaxy Messier 87. What the image showed was not the event horizon itself, but a dark central shadow surrounded by a bright ring of emission from hot plasma near the hole. So yes, in one sense, a black hole is black because light cannot escape from inside the event horizon. But the physical story is richer than the name suggests. The black hole can have temperature, and the region around it can be dazzlingly bright. That is why the phrase perfectly black is misleading. It confuses the causal structure of the horizon with the observational behavior of the full system. Myth 4. You are instantly destroyed the moment you cross the event horizon. For many black holes, especially supermassive ones, this is false. The event horizon is not a wall of fire. It is not a material surface. You would not even notice crossing it. For a supermassive black hole, you could pass through the event horizon and survive for a while before reaching the singularity. The event horizon is a mathematical boundary. It is the point of no return. Once you cross it, you can never escape. But crossing itself does not harm you. There is no physical barrier, no membrane, no discontinuity. Spacetime is smooth at the horizon. An astronaut falling through would feel nothing unusual at the moment of crossing. What determines whether you survive depends on tidal forces. Tidal forces arise from the difference in gravitational pull across your body. If your feet are closer to the black hole than your head, your feet experience stronger gravity. This difference stretches you. If the difference becomes large enough, you get spaghettified. Your body is pulled into a long, thin strand. The tidal forces depend on the mass of the black hole. For a stellar mass black hole with about 10 solar masses, the tidal forces near the event horizon are devastating. You would be ripped apart before or near the horizon. But for a supermassive black hole, the event horizon is much farther from the center, and the tidal gradient there can be surprisingly mild. That means the horizon can be crossed intact. Inside the horizon, you continue falling. The singularity is still ahead in your future. How long you survive depends on the mass and spin of the black hole and on the exact path you take. For a sufficiently large black hole, there can be a real interval between horizon crossing and destructive tidal effects. There is another strange layer to this. To a distant observer, you never seem to cross the horizon. Your image redshifts, dims, and appears to slow down more and more as you approach. But from your own perspective, you cross in finite time. Both descriptions are valid within their own reference frames. This is not a contradiction. It is one of the standard consequences of relativity. The key point is that the horizon is not identical to destruction. For some black holes, the real danger comes much deeper inside, when tidal forces rise to fatal levels. Myth 5 time stops at the event horizon. This is one of the most persistent simplifications in popular science. You will hear people say time stops at the event horizon. Clocks stop ticking, motion ceases, but this is false. Time does not stop. Time dilation becomes extreme, but time continues to flow. Time dilation means that clocks run at different rates depending on gravitational field strength. A clock deep in a gravitational well runs slower compared to a clock far away. This is gravitational time dilation, confirmed by experiment and even relevant for GPS satellites. Near a black hole, the effect becomes extreme. A clock hovering very near the horizon runs enormously slow relative to a distant observer. But that does not mean time stops for the clock itself. From the perspective of someone falling into a black hole, their watch continues to tick normally. They experience finite proper time. They cross the horizon in a finite interval of their own time. The confusion comes from the perspective of a distant observer using Schwarzschild coordinates. In that coordinate system, the infalling person's image appears to slow down and asymptotically freeze near the horizon. The light from that person becomes more and more redshifted. Eventually, the signal becomes too faint to detect. To the distant observer, the person never seems to cross. But that is an observational and coordinate effect, not a statement that time physically stops at the horizon. This is why physicists distinguish between coordinate time and proper time. Coordinate time depends on the chosen reference frame and coordinates. Proper time is what a local observer actually experiences along their own path. In better coordinate systems, such as Eddington-Finkelstein or Kruskal-Shekker's coordinates, the horizon is not a place where time suddenly stops. The geometry remains smooth. The infalling observer passes through without encountering a singularity at the horizon. There is another reason the slogan "time stops" is misleading. Hawking radiation in the semi-classical picture is associated with the horizon. If time literally stopped there in every meaningful sense, it would be very hard to describe any dynamical process related to evaporation. So the cleaner version is this. From far away, signals from a falling object become infinitely delayed and redshifted at the horizon. But from the falling object's own perspective, time continues, the crossing happens, and the fall inward goes on. Myth 6. Black holes live forever. At first glance, that sounds reasonable. If nothing can escape, how could a black hole ever disappear? But Hawking radiation changes that picture. Black holes evaporate. They have finite lifetimes. The evaporation time depends strongly on mass. A black hole with roughly the mass of the Sun would take on the order of 1067 years to evaporate completely. That is vastly longer than the current age of the universe. So for all practical human and even stellar timescales, astrophysical black holes are long-lived. But long-lived is not the same as eternal. Small black holes evaporate much faster than large ones. As a black hole loses mass, its temperature rises and the evaporation speeds up. In the final stages, the process becomes dramatically more intense. This leads to one of the most important conceptual shifts in black hole physics. A black hole is not an eternal prison outside thermodynamics. It is a thermodynamic object that exchanges energy with the universe. That has huge consequences. If black holes evaporate, then any full theory of physics has to explain what happens to the information associated with what fell in. That is one path into the information paradox. In the far future, after stars burn out and galaxies evolve into much quieter structures, black holes are expected to dominate the inventory of compact objects for enormous spans of time. But even they do not last forever. The largest supermassive black holes may survive for absurdly long durations, up to around 10–100 years in rough estimates, but not indefinitely. Eventually, even they should evaporate if the standard semi-classical picture remains valid. So the statement that black holes live forever is wrong in principle, even if for the largest astrophysical black holes the timescales are almost beyond imagination. Myth 7. All black holes are roughly the same. Black holes come in an enormous range of sizes and types. Stellar mass black holes range from a few solar masses to perhaps a few hundred in special cases. Intermediate mass black holes, if and where they exist, sit between stellar and supermassive scales. Supermassive black holes range from hundreds of thousands of solar masses to billions or even tens of billions. That mass range alone changes almost everything. The event horizon of a stellar mass black hole is measured in kilometers. The event horizon of a supermassive black hole can be comparable to the size of a planetary system. Density also behaves in surprising ways. A small black hole can have an average density comparable to nuclear matter. A huge supermassive black hole can have a much lower average density within its horizon because the volume grows faster than the mass. Spin matters too. A non-rotating black hole is described by the Schwarzschild solution. A rotating black hole is described by the Kea solution. Rotation changes the shape of the horizon, creates an ergosphere, and alters the behavior of nearby matter and light. Charge can matter in theory, although astrophysical black holes are expected to be nearly neutral overall, because surrounding plasma cancels large charge imbalances quickly. Even so, the mathematical families of black hole solutions include charged versions. Environment matters as well. Some black holes sit in quiet regions with very little nearby material. Others are embedded in active galactic nuclei and feed through luminous accretion disks. Some launch spectacular jets, others are comparatively silent. Formation history also differs. Stellar mass black holes usually come from the collapse of massive stars. Supermassive black holes almost certainly involve different growth channels and seed populations. Primordial black holes, if they exist, would have formed in the early universe rather than from stars. So the phrase black hole refers to a family of objects defined by a certain causal structure, not a single standard object that behaves the same in Myth 8. Spaghettification happens the instant you approach a black hole. Spaghettification is real, but when and where it happens depends entirely on the black hole's mass. For stellar mass black holes, you get spaghettified well before reaching the event horizon. For supermassive black holes, you can pass through the event horizon intact and get spaghettified much later. Spaghettification occurs when tidal forces exceed the structural strength of your body. Those tidal forces depend on how quickly gravity changes from one part of your body to another. That is why the gradient matters more than the absolute gravitational pull. For a black hole with roughly the mass of the Sun, the tidal forces near the horizon are catastrophic. You would be stretched and compressed into a long, thin strand long before reaching the central region. That is the classic image people associate with black holes. But for the black hole at the center of our galaxy, Sagittarius A, the tidal forces at the event horizon are much gentler. The horizon is so far from the center that the gradient there can be relatively small across a human body. That means crossing the horizon is not necessarily the spaghettification moment. For a supermassive black hole, that might happen much deeper inside, closer to the singularity where the curvature becomes extreme. There is another subtlety. Spaghettification is not a uniquely black hole phenomenon. Tidal forces exist anywhere gravity varies strongly over distance. The moon raises tides on Earth. Jupiter can tear apart comets that pass too close. Black holes simply give us the most extreme version. The name also misleads a little. You are not only stretched along your length, you are also compressed sideways. The process is a combination of stretching and squeezing caused by the geometry of the gravitational field. So yes, spaghettification is real, but no, it is not a universal instant event that happens the moment you get near any black hole. The black hole's mass determines whether it happens outside the horizon, near the horizon, or much farther inside. Evaporation, information, and the growth of giants. Once the basic picture is in place, black holes become even more interesting. They stop looking like simple gravitational traps and start behaving like thermodynamic systems. They have temperature, they have entropy, they can evaporate. And once you admit that, a deeper puzzle appears almost immediately. If a black hole can evaporate, what happens to the information about everything that fell in? This is where black holes stop being only an astrophysical topic and become a foundational problem in theoretical physics. The next group of myths moves from classical gravity into quantum gravity territory. We will talk about Hawking radiation, the information paradox, the origin of supermassive black holes, and the difference between mathematical convenience and physical reality. We will also look at how black holes move, how singularities are interpreted, and why the event horizon is not the kind of surface most people imagine. At this stage, black holes stop being objects you merely observe from the outside. They become probes of the universe's underlying rules. Myth 9: black holes violate the laws of physics by destroying information. This is the black hole information paradox, and it is one of the deepest puzzles in theoretical physics. For decades, physicists argued over whether black holes destroy information. In ordinary quantum mechanics, information is not supposed to disappear. It can be scrambled beyond practical recovery, but the underlying evolution remains unitary. The problem appears when you combine that principle with Hawking radiation. If a black hole forms from some complicated matter distribution and later evaporates into perfectly thermal radiation, then the detailed information about the original state seems lost. That would be a major problem. It would suggest either that black holes destroy information or that our semi-classical description of evaporation is incomplete in a deep way. For many years, Stephen Hawking argued that information really was lost. Most theoretical physicists became convinced that this could not be the final story. In 2004, Hawking publicly conceded that information is likely preserved. But saying information is preserved is not the same thing as showing how. That is the hard part. In recent years, theoretical work involving entanglement, page curves, quantum extremal surfaces, and so-called islands has made major progress. The basic idea is that Hawking radiation may not be perfectly random after all. Tiny correlations in the radiation, accumulated over the full lifetime of the black hole, may encode the information in an extremely scrambled form. That would mean black holes do not violate quantum mechanics. They do not destroy information. They scramble it so violently that recovery becomes fantastically difficult, but not impossible in principle. This is why the information paradox is so important. It is not just about black holes. It is about whether quantum mechanics and gravity can coexist without contradiction. And at the moment, the best modern view is that information is probably preserved, though the full microscopic mechanism is still an active area of research. Myth 10. Supermassive black holes formed from collapsed stars, just like stellar mass black holes. Modern astrophysics strongly suggests this is not how the largest black holes formed. Stellar mass black holes form when massive stars exhaust their nuclear fuel and collapse. But supermassive black holes with millions or billions of solar masses cannot form this way. There is simply not enough time for ordinary stellar remnants to grow into the earliest giant black holes we now observe. The James Webb Space Telescope has revealed surprisingly massive black holes and active galaxies very early in cosmic history, only a few 100 million years after the Big Bang. That suggests the seeds of supermassive black holes were already substantial. One leading idea is direct collapse. Under the right conditions in the early universe, a massive gas cloud may have collapsed into a black hole without fragmenting into normal stars first. That would produce a much larger initial seed than a typical stellar remnant. Another possibility is that unusual populations of very massive early stars helped seed rapid growth. Primordial black holes have also been discussed as possible seeds, though that remains speculative. Whatever the detailed answer turns out to be, the biggest black holes almost certainly did not begin life as ordinary stellar corpses and simply follow the same path on a larger scale. Their origin appears to involve different channels and possibly special conditions in the young universe. That is why the origin of supermassive black holes remains tied to the broader question of how the first galaxies formed and evolved. Myth 11. Black holes are stationary objects anchored in space. Black holes move just like any other massive object. They orbit galactic centers. They participate in binaries. They merge. They can even be kicked across space after a merger. Stellar mass black holes in our galaxy orbit the Milky Way just as stars do. Some are found in binary systems with ordinary stars, and their motion is part of how we detect them. In such systems, The black hole and the companion orbit their common center of mass. Black hole mergers provide the most dramatic example. When two black holes spiral together, they emit gravitational waves. If those waves are emitted asymmetrically, the merged remnant can receive a recall kick. Depending on the system, that kick can be large enough to move the new black hole far from its original location, and in some cases, possibly even out of a small galaxy. Supermassive black holes also move during galaxy mergers. When two galaxies collide, their central black holes do not merge instantly. They first sink through the surrounding stars and gas, form a binary, and gradually spiral inward. The idea that black holes are anchored probably comes from imagining them as immovable cosmic wells. But a gravitational field does not pin an object to spacetime. A black hole is a localized mass-energy configuration, and like any such object, it can move under gravity and momentum. So black holes are not fixed holes in the universe. They are dynamic participants in cosmic structure. Myth 12. The singularity at the center of a black hole is a physical point in space. The singularity is one of the most misunderstood ideas in black hole physics. In classical general relativity, it marks the point where density and curvature become formally infinite. But in physics, infinities usually signal that a theory has reached the edge of its validity. That is why most physicists do not treat the singularity as a simple literal object sitting there like a tiny hard ball. They treat it as a warning sign that general relativity is incomplete in that regime. At sufficiently small scales and extreme curvatures, quantum effects should matter, but general relativity is not a quantum theory. So when the classical equations produce a singularity, they are telling us that quantum gravity must eventually take over. There is another subtlety. For an infalling observer inside the horizon, the singularity is not merely a point somewhere ahead in ordinary space. In the causal structure of the interior, it behaves more like an inevitable future boundary. That is why saying the singularity is a place in space can be misleading. In the standard interior picture, reaching it is as unavoidable as moving forward in time. Different candidate theories of quantum gravity offer different ideas. Some replace the singularity with a bounce, some with a new quantum phase, some with a smeared structure, and some with something more radical still. But the shared lesson is this: the singularity in the textbook solution should not be mistaken for the final physical word. It marks the failure of our present description, not the end of the scientific story. Myth 13. Black holes are perfectly spherical. Only the simplest idealized black holes are perfectly spherical. A non-rotating black hole in general relativity is described by the Schwarzschild solution, and in that case, the horizon is spherical. But real astrophysical black holes are expected to rotate because the matter that formed them carried angular momentum. Rotation changes the geometry. A rotating black hole is described by the Kea solution. In the Kea case, the horizon is no longer a perfect sphere in the naive sense. The geometry becomes more complicated, and outside the horizon appears the ergosphere, a region where spacetime itself is dragged around by the hole's spin. That frame-dragging effect has major consequences. It changes how matter orbits, how light propagates, and how rotational energy may be extracted in principle. It also affects the appearance of the black hole environment. Observationally, rotation matters enormously because it influences the structure of the accretion flow and the launching of powerful jets. In fact, some of the most energetic black hole systems are thought to depend strongly on spin. So the perfect sphere picture is a teaching model. It is useful at first, but it is not the whole astrophysical reality. Light merges and black holes in the living universe. Black holes are often introduced as dark, silent objects. In reality, they can be among the most dynamic and observable engines in the cosmos. They bend light, organize accretion flows, launch jets, merge with each other, reshape galaxies, and announce those mergers across the universe through gravitational waves. The modern age of black hole astronomy is not built on imagination alone. It is built on repeated observation. In this section, we shift from internal logic to visible consequences. We will look at photon spheres, primordial black holes, merger dynamics, gravitational waves, feedback in galaxies, and the large-scale role black holes play in cosmic evolution. If part III made black holes stranger, part III should make them feel more real. Myth 17: light can orbit indefinitely at the event horizon. Light does not orbit at the event horizon itself. The relevant structure is the photon sphere, which lies outside the horizon in the non-rotating case. At the photon sphere, light can follow circular orbits, but those orbits are unstable. A small perturbation sends the photon either outward to infinity or inward toward the black hole. That is very different from saying light somehow sits and orbits F.